Hello and welcome back. Today we're going over section 1.4, which is going to take us through lines. We'll also get to see a couple of proofs again. So for starters, we will consider the function f of x equals mx plus b. So I'm going to ask you to just pause it real quick, find f of 0 and f of 1. Okay, welcome back. So f of 0, m times 0 plus b. So f of 0 is equal to 0 plus b. F of 0 is equal to b. That's equivalent, of course, to having the order pair 0b. F of 1, m times 1 plus b. So f of 1 is m plus b. And that's as far as we can take that one without knowing anything more about m or b. So one thing we just proved here was that when we're in function notation, we have a linear. 0b is indeed our y-intercept, since that happened when x is 0. Now we've shown that for the general case, so we do know that that is true in general. We can also use these two to show that the slope is indeed just the m that we're expecting. So slope, remember, is change in y divided by change in x. So our change in y, our y values, we had an m plus b and we had a b. Change in, remember, is subtraction. Change in y divided by change in x. Our x is changed from 1 to 0. So up top, m plus b minus b is m. On the bottom, 1 minus 0 is 1. M divided by 1 is indeed just m. So we know we have a slope equal to m. So some properties that we already know, but now we've actually proven them. Notice slope is undefined for delta x equals 0. But if delta x is 0, basically your x values were the same for two different points. That implies we had a vertical line instead of either a horizontal line or a slanted line. Now we can also get our useful point slope form out of just our general knowledge about slope. Slope is change in y times change in x. If I multiply both sides by change in x, delta x divided by delta x is 1. 1 times anything is that anything, and we get change in y is the slope times our change in x. Change in, remember, is always a subtraction problem. So just a couple quick little review problems with that. So find equation of line containing, we'll use -7, 3 and 6, -1. So no matter what version that they want us to end on, we do need to figure out the slope. So slope, as always, change in y divided by change in x. So anytime I'm using substitution, I like to use parentheses. It goes from being helpful and a good idea here to being a written in stone requirement here. So it's a good idea just to do that in general. So 3 and 1 upstairs, -7 minus 6 downstairs. So our slope here then is -4/13. So then we just say, okay, change in y is the slope times change in x. And we can use either point. It doesn't matter which one we use. And you've seen that the last couple of courses, so we're not going to spend tons of time on that. So arbitrarily, I'll use the first one. So y minus 3 is our slope times x minus negative 7. So y minus 3 is negative 4/13 of x. I have 1, 2, 3 negatives, and result is negative. So 28/13. And where we go from there kind of depends on what we're looking for. If we want the sort of standard form, we can clear the fractions and get all the variables on one side. So I'll put a little asterisk by this. Where we go from this step depends on what we want to do next. So if they ask for standard general form, we would clear the fraction. So we'll multiply both sides by 13 if we're doing that. So 13y minus 39 is negative 4x minus 28. And we just add 4x on both sides, add 39 on both sides. So we have 4x plus 13y is worth, that would be positive 11. If instead they asked us for function notation from this step, we want to get the y by itself, so I would have just added 3 to both sides. And remember, 3 over 1 is the same as 39 over 13. Think of getting that common denominator between 13 and a 1. LCD is 13. Multiply the 3 over 1 top and bottom by 13. So y is negative 4/13 of x plus 11/13. And if they ask for a function notation, we do still have to give it a name. Call it f of x, g of x, something of x. So which version they want, they'll sometimes ask for one, sometimes the other. Now, as far as equations for the two special cases of a horizontal line or a vertical line. Horizontal line, and just sort of make a quick rough sketch of one. And let's say that this point is at 0C. Then a point over here would be at, well, let's say 1C. And a point over here, maybe 10C, negative 3C. Every point on the horizontal line here is going to be something comma C. It's the y value that stays put, and it stays at value C. Vertical, of course, the one with the undefined slope. It's where the x values remain unchanged. We'll call this maybe D0. So up here we have maybe D7, and so on. All of those points are going to have x equals whatever real number D in common. So there, C and D, we're in the set of reals, of course, since we're in the xy plane. Alright, so next up we talk about parallel lines. That's pretty quick. We'll introduce a little bit of notation, though, that will help us out with the more involved perpendicular lines, parallel lines. So L1 is shorthand, of course, for line 1, L sub 2, line 2. Those are parallel if one of two things happens. Slope for line 1 is equal to slope for line 2, or possibility number 2, L1 and L2 are both vertical. So if we have an undefined slope, we can't say it's equal to something else, but if they both have undefined slopes, they're vertical lines and therefore must be parallel. So same slope or both vertical, you got parallel lines. So perpendicular is where we get a little bit more involved. In this one, we get to play with a little bit of a proof too. And now let's just start a fresh page for it too. So two non-vertical lines. So we're tossing out that case of undefined slope. Are perpendicular if and only if. You'll see mathematicians abbreviate this as IFF. If you see IFF, that's replacing those four words. It's basically two if-then statements. If and only if, product of their slopes is -1. So what this means is we have two if-then statements. If we have two non-vertical lines that are perpendicular, then we know the product of their slopes is -1. We also have, if the product of the slopes of two lines is -1, then they have to be perpendicular. So let's take a look at a proof for this. So we'll go sort of forward first. Let L1, L2 be two non-vertical lines. And we want them to be perpendicular. Common shorthand for perpendicular. So I'm drawing the T-square tool. Another common abbreviation coming, so we'll give you the long version first without loss of generality. We'll see that as WLOG. So it means I'm going to do something that will simplify my calculations, but it would still work anywhere without the simplification happening. So we're going to let L1 and L2 meet at the origin. That's going to make our work a little bit easier. But that's not to say that they have to meet at the origin. It just means our demonstration is easier at the origin. So we're going to make a quick sketch of what we have. So here we are in the XY plane. We have two lines and we have them meeting at the origin. And we're claiming that they are perpendicular. So I'll draw them as sort of close as I can, freehanding in to a nice pretty 90-degree angle there. So that dot is happening on the origin, 0, 0. And what I'm going to do is just go out to 1 for each of them. So line 1 is going to be y equals m1 times x. Why not a plus b on there? B is 0. We had them meet at the origin. Line 2 then is y equals m2 times x. So if x is worth 1, m1 times 1 is still m1. If we make this guy our line 2 and go to an x value of 1, y is m2 times 1, y value of just m2. So we said that this is a pair of non-vertical lines that are perpendicular, which means they meet at a 90-degree angle, which means we just drew a right triangle. So this has to obey the Pythagorean theorem. So if we call this A and this guy B, and we'll call this guy C, A squared plus B squared has to equal C squared. Well, let's look at A, distance formula. A squared is 1 minus 0 is 1, so 1 squared plus m1 squared. B squared, 1 squared plus m2 squared. Now, even though m2 here would be a negative value, at least the way that I've drawn it, negative times a negative still kicks us over to a positive. So we can just leave it in that format. And finally, our friend Charlie here is just m1 minus m2. So Charlie squared is m1 minus m2 squared. So then 1 squared plus m1 squared, a squared, plus 1 squared plus m sub 2 squared, b squared, equals c squared. m1 minus m2 quantity squared. So just a little bit of simplifying on the left side. We have 2 plus m1 squared plus m2 squared. And on the right hand side, we'll FOIL this guy out. So 2 plus m1 squared plus m2 squared is m1 squared, first times first. Then we have minus m1 m2 minus another m1 m2, so minus 2 of the m1 m2s, and plus m2 squared. So what does that do for us? Well, we have m1 squared on both sides. We have m2 squared on both sides. So now we have 2 is negative 2 m1 m2. Divide both sides by negative 2. And m1 m2 is negative 1. That's the then part we were trying to show. So we started off saying we have two perpendicular lines, non-vertical, and we showed that then the product of their slopes must be negative 1. If this were just an if-then proof, we'd be done, but this was an if and only if proof, so now we start the other way. We start assuming that we have a product of negative 1 on the slopes and show that the lines have to be perpendicular. It's going to be a similar setup, though. So for the second part, suppose m1, m2 is negative 1. Well, then m1 is negative 1 over m2. Without loss of generality, L1, L2 meet at the origin. So this time I'm not going to draw my little right angle symbol on here since I haven't proven that that's correct yet, and we haven't made the assumption that we have a right angle. We're proving that we have to have a right angle. We do know, though, that we decided to let these guys meet at the origin. And since we let them meet at the origin, line 1 is still y equals slope 1 times x, and line 2 is still y equals slope 2 times x. By substitution, though, we can say that y is negative 1 over m2 times x for line 1. Just replacing m1 by what we said m1 was the same as. So on line 1 here, if we go out to where we have an x value of 1, we have a y value of negative 1 over m sub 2. Down here on line 2, if x is 1, y is m2. Not an exponent, subscript. My apologies. M sub 2. So if I want to know if this red triangle here is a right triangle, I can again label A, B, and see, does this indeed follow the Pythagorean theorem? A squared plus b squared equals c squared. So let's start by finding a squared. So that's just the distance between these 2 points. So 1 minus 0 is 1, so we have 1 squared plus 0 minus a negative 1 over m2 turns into positive 1 over m2. And we're, of course, squaring that. B squared, 1 squared, 0 to 1, plus m2 squared. C is the difference between those. So we'll just say m2 minus negative 1 over m sub 2. And we're squaring it, so it doesn't matter which one went first. Squaring it's going to kick it over to being non-negative. So this time I'll put a little question mark over my equal signs because I don't know that they're equal. But I want to know, does a squared, so 1 squared is just a 1, is 1 plus 1 over m sub 2 squared plus b squared. 1 squared is still 1. m2 quantity squared is just m2 squared. Is this equal to c squared? I'm going to take the liberty of expanding it a little bit now. Minus a negative, we'll flip it over to a plus. So left-hand side, not much simplifying to do. We can put the 1 and 1 together. So we have 2 plus 1 over m2 squared plus m2 squared. Right-hand side, we can FOIL out again. So m2 times m2 is m sub 2 squared. m2 times 1 over m2 is a 1. Inside times inside, 1 over m2 times m2 is 1. A number times its reciprocal will give you a 1. And finally, L, the last, 1 times 1 is 1. m2 times m2 is m2 squared. So left-hand side, no more simplifying to be done. Just bring it on along. Right-hand side, 1 and 1, sure enough, there's our 2. We have our 1 over m2 squared, and we have our m2 squared. So you just get 2 equals 2 since both of those guys canceled out. We get a true statement then. This is an identity. This is always true. So therefore, L1 must be perpendicular to L2 because the Pythagorean theorem did hold. And that's the end of our proof. We can show the reader that with a nice little square there. And then we'll just run through one quick practice one. And then we'll get to the homework. So find an equation of line perp to 4x plus 5y equals 7 containing -1, 6, and we'll go with function notation. So they wanted it perpendicular to this line. That means I need the slope of that line, so I'll get this guy into slope-intercept form. So we'll subtract 4x on both sides. 5y is negative 4x plus 7. Divide both sides by 5. So y is negative 4/5 of x plus 7/5. So the slope of that line is negative 4/5. We want the perpendicular slope to end up with a negative 1 when we multiply it with the original slope. So that means that m perp would have to be 5/4. So negative times a positive kicks us to a negative, and 4/5 and 5/4 multiply to 1. So basically we want this slope with that point. So then we're just doing change in y is slope times change in x. So y minus 6 is our slope times our change in x. So y minus 6 is 5/4 of x, minus a negative turns into a plus, and 1 times 5/4 is 5/4. So I'll add 6, which is 24/4. Think of 6 over 1, so y is 5/4 of x plus 29/4, and then just give it a name, f of x, g of x. Pick a letter, make it of x. All right. So there is our line with the given characteristics in function notation. So in 1-4, if you're going with the book homework, I would try out 1 to 10 all, 11 to 107 every other odd. So every fourth problem, do 11, skip 13, do 15, skip 17, and so on. 113, 115, 123, 124, and 130, and then I'll try to find some rough equivalents in the MyMathLab for those of you doing the MyMathLab problems instead. All right, if you have any questions, please feel free to get in touch with me. Otherwise, I'll see you next time. Stay safe out there.